The next presentation is a generalized multiport representation of power systems using ABCD parameters for harmonic stability analysis, which is going to be presented by Aleksandra Lekic. Aleksandra received bachelor, master, and PhD degrees in electrical engineering from the University of Belgrade. And she has been with the School of Electrical Engineering of this university till 2019. And in 2019, she was with KU Leuven as a postdoctoral researcher. And now she works as an assistant professor at TU Delft in the Department of Intelligent Electrical Power Grids. So, Aleksandra, please, when you want.
Okay, do you see my screen?
Yes, perfect.
Okay, thank you very much. Thank you for a nice introduction. I will present you a paper which is done at KU Leuven together with Institute Energiewheel. This work is supported through Neptune project. I want to see if my camera is on. Yes, I will start the video. Sorry. I will go to the next slide. The paper deals with harmonic stability analysis. Of course, we know with deployment of renewable energy sources, we have increased need of integrated power electronics. And these power electronics can cause harmonic stability problems. This problem can be analyzed by checking second things, frequency dependency of each power system component, and we should construct a detailed power converter model which incorporates all controlling methods inside, so all the inner and outer controlling loops. At this point, stability analysis can be carried on only looking a small portion of the power system from AC side or from DC side. There are just a little bit of research done that considers both sides of the power system. The approaches are normally just harmonic state space analysis and impedance-based analysis. In this work, we have used impedance-based modeling. All our power system components have detailed frequency-dependent models. They are considered like multiport elements in the Laplace domain or Fourier transform domain. We have defined a procedure for determining an equivalent multiport description. This procedure will be demonstrated on one point-to-point hybrid power system, and it is demonstrated through a simulation written in Julia programming language. Why did we start with ABCD parameters? Here is the reason. Every component can be described using parameters. So we know about impedance, admittance, hybrid parameters. But here I have two examples. Figure A shows the example where we cannot define impedance parameters because we don't have impedance at the input side. It is open connection. Figure B shows the example where we cannot define admittance parameters. That can be solved using hybrid parameters, but they are not really intuitive by definition. So we chose to do it with ABCD parameters. ABCD parameters are really nice because, first of all, you have a physical dimension. So you use only input and output voltages and currents. They provide you a direct interconnection between input and output voltages and currents with the equation in the matrix form written on this slide. The other thing why they are really good is that from ABCD representation of one component or of one portion of the system, power system, we can check visible impedance. For example, here you see one portion of multiport component or multiport power system described with ABCD parameters. And if we close the output with some impedance, here it is a diagonal impedance, consider ZT. We can easily determine input impedance in the system. On the other hand, if we close at the input side with that impedance ZT, we can find the impedance visible from the output side. So those are those simple formulas written on the slide. On the other hand, we can easily define equations that should be solved in the system using a modified nodal analysis approach. One thing I should mention, this input and output and impedance are really valuable for impedance-based analysis, which we will perform in our work now. More details about ABCD components is that the series connection of the components can be easily given with the formula, just multiplication of matrices. It is basically cascading of the components. Parallel connection is given with more difficult formula, a bigger formula. And that's why we decided to describe our system using that modified nodal analysis approach and solving this system of equations. With X are given all our variables like node voltages, input currents, and the components currents that we want to know in the system via output voltages and voltages of grounds, just zeros. M and N are coefficient matrices. What we can see on this figure is just that every power system we can just take one portion. There are here multiple components. We can say, okay, we want to consider that number of components, and we define input and output nodes. And from there, we can find equivalent ABCD representation by solving this system of equations from this slide. And afterwards, we can see what is input and output impedance. So this is what I described. So we find the equivalent ABCD description of the subnetwork. If we want to find the input or output impedance, we just put a virtual ground at one end. Afterwards, the impedance visible from some nodes of the subnetwork can be estimated using simple formulas from the previous slides. And what we want to perform is just to find out if the system is stable. Then the stability analysis can be run by estimating a feedback transfer function of the equivalent impedance of the network visible from power converter and admittance visible inside of the converter. From there, you can use a Nyquist plot or border plots for detailed stability analysis. In the next slides, I will just show a couple of power system components, how they can be modeled using ABCD parameters. So here we have impedance model. This impedance model can be used for all inductors, capacitors, resistors, modeling loads, even shunts can be modeled with this impedance model. What we can see in the figure is how interconnections are defined. And for all of those interconnections, we can form the matrices in ABCD domain by solving this equation, like inverse of matrix M1 times matrix M2 gives us ABCD representation of this impedance. What about transformer? It is written on this slide. This is only a single phase transformer, but we can consider three-phase transformers in different configurations. So Y delta, Y Y, delta delta. It is just a combination of the equations given here. ABCD equation for this single phase transformer is initially provided in PhD thesis done at KU Leuven with Alejandro Bayo-Salas. For cables and overhead lines, well, ABCD model is good known. It is given on this slide, and we tried in our codes written in our codes to actually support all combinations in overhead lines and cables. Actually, we can provide the exact same results that PSCAD gives. For example, all types of conductors, bundles, and etc. Series impedance and shunt admittance used in the calculations are given on this slide. Here we can see one example of short connected overhead line. This example is compared with PSCAD, and it gives really good accuracy of our simulation. It shows good accuracy. For the cables, also we support multiple layers. Multiple layers for conductors, then one layer for semiconductor, and multiple layers for insulators. And here we can see one example of also short connected cable. It also gives really good accuracy compared to PSCAD. The most important part of this work is an MMC model. For PSCC paper, we have focused on the model of an MMC considered from DC side. Few loops are considered, so circulating current, output current control, and the active power control. Also, PLL is incorporated. This MMC model is given with the formulas from this slide. It is considered like an impedance described with this formula. So you can see formula for admittance of an MMC looked from the DC side. In the further work, what we have at the moment, we have a MMC model that can be described with admittance looked from AC side in DQ frame, also from DC side, and all the interconnections between DC and AC sides are now supported. Here on this slide, we have one example of the point-to-point hybrid power system. On this example, we have two MMCs, and they are interconnected with a mixed overhead line cable. In this example, because our code runs symbolically, we show what the code gives as an equivalent impedance, where A, B, C, and D symbols are actually symbols of ABCD matrix of this mixed overhead line cable connection. And ZMMC2 is impedance visible when you look from DC side into MMC2. On the last slide here, we can see Bode plots of the feedback transfer function from this point-to-point system. So it is admittance of MMC1 times impedance, equivalent impedance. We can see here that from this diagram, easily it can be determined if the system is stable or not stable. And what is a good advantage of the proposed work is that it runs rather fast. Here we can see that it runs in 0.61 seconds in Julia programming language, which is really short comparing to available simulators. For example, for just one MMC converter in PSCAD, we took almost a day to get admittance visible from DC or from AC side. So this is really good result. We can see from the previous slides that these ABCD parameter components can be successfully used for harmonic stability analysis, and they are given in the frequency domain, which is also, from our point of view, good. Thank you for your attention. So I would like to ask you if there are some questions.
Okay, thanks a lot, Aleksandra, for your presentation. Any question? Yeah, 1 second. Sao Juan is asking why we need to replace the impedance representation by ABCD representation.
Okay,
No.
the entire system is, I'm sorry, yes, the entire system is formed in ABCD domain. So every component should be defined in using ABCD parameters, and that's why we are replacing also impedance besides everything else with ABCD parameters.
Yes. He says that, are you saying the question and answer panel, Aleksandra?
I opened it, but yes, I don't
But you can see
anymore.
the, you can't see the questions. Can you see the questions?
At the moment, yes, I can.
Yes, probably you can read it.
Yes, the ABCD parameters are. No, we didn't say that it is faster than a representation using other type of parameters. The thing is, this representation is suitable to represent all types of components. I gave you two examples when first impedance parameters cannot be defined, and the second one is when admittance parameters cannot be defined. ABCD parameters can be defined in all cases. Like hybrid parameters also, but they are intuitive. And the simulation runs approximately the same speed like Y parameters. But what we present in this work is that we first of all can cover all cases, and afterwards that our tool that we designed is rather fast because interconnections are fast, and we get symbolic equations which are used. So
Thanks a lot for your answer.
thank you.
I would like to ask you what happened with the computational cost in other networks, in larger networks.
In
You have
larger
analyzed,
networks,
yeah, that's the question.
well, now we have analyzed not so large networks, but let's say that we tried multi-terminal DC networks with, for example, 4 converters, and we have some kind of master-slave controlling methods. In this case, it runs in a couple of seconds. So it's something like 20, 30 seconds.
Mm-hmm. Okay. Thanks a lot. Thanks a lot for your presentation. Okay. Any other question from the audience? Perfect.